Our group is called Papa Mohanty and consists of Cheston, Gonzalo, Jerry, Andrew, Camille, Milton, Rachel, and Yen. Today, we will be presenting on our green infrastructure mitigation of Gompers Elementary School. Our site is Gompers Elementary School, which is located in a low-income community in Lakewood, California. The school consists of mainly impermeable surfaces with only 10.4% of the usable space being green space. The asphalt and other impermeable surfaces contribute to urban heat and increase in runoff as stormwater cannot be infiltrated. Therefore, our goal for this project is to implement green infrastructure to decrease the local temperature, increase capture and infiltration of stormwater runoff, and improve student engagement and development.
So some of the questions we would like to answer before we get started with the analysis and details. The first being, are some green infrastructures better suited for certain climates? Since our site is located in Los Angeles, which is a quite dry climate, we need to consider this as a factor. And second question being, will these improvements actually improve runoff infiltration? So we quantified this question through infiltration, modeling, and calculations. And then will the installation of green infrastructure improve students' academic performance, specifically like cognitive ability and test scores? And the last question being, how much will these improvements cost? So we were able to quantify this question through a cost estimate calculation.
Our first hypothesis aims to quantify the effects of green roofs and solar panels on our building. And we say that green roofs and solar panels is a cost-effective strategy that will reduce surface temperatures, produce clean energy, increase energy efficiency, and retain and reduce stormwater runoff.
When the solar panel is the only rooftop design, 2.5 to 200 kilowatt system was calculated to be needed to cover all the energy costs, and the payback period is about 4 years. The calculation table is right under here. We do expect that the solar panel will lower the roof temperature and reduce cooling energy, but they were found that the impact is not significant. So the decision about the amount of solar panels mainly depend on the budget. Picture right here is a case study of the temperature reduction, and you can see the maximum difference is only about 6K.
So looking into green roofs, we found that they had a potential to reduce indoor temperatures by around 2 degrees Celsius, which means less AC and heating required for the school. We also found that green roofs were able to retain 40% more stormwater than asphalt, leads to less pollution and erosion of streams, lakes, and river runoffs. We also found that green roofs could have the potential for air pollutant capture. We also analyzed 2 case studies of extensive or shallow green roofs in Denver, Colorado. The first one in the right is the green roof at EPA Region 8 headquarters, and the second one is for Elkins Meadow residents. For our model, we wanted to implement both of these models into the school, where the first roof, or the EPA roof, will be for larger roofs between 2,000 and 20,000 square foot, while the second model will be for modeling the Elkins Meadow residents, which is less than 2,000 feet. And both of these models use sedums or succulents that are really drought resistant and great for surviving the arid, dry climate of California. And below is a model of the proposed green roof plan.
From our results, we decided that we wanted 42% of the roof to be covered in solar panels, as this would cover all the energy costs and provide energy savings in the long run. For the rest of the roof, we wanted green roof, and following the two case studies we looked at, we will be implementing the green roofs on various parts of the building with smaller areas using one type, whereas the larger areas using the EPA type. And other considerations are that solar panels placed directly on top of the green space actually may perform better. So in our design, we may incorporate this.
So to conclude, the results and discussion for hypothesis 1. So implementing a combination of green roofs and solar panels is a cost-effective hybrid strategy that will reduce temperatures of ground surfaces, recapture or produce clean energy, and increase energy efficiency. And we were able to quantify this with the previous energy consumption calculations.
Great. So for hypothesis 2, it's a two-part hypothesis we're looking at, which considers number 1, the relationship between green spaces and their effects on cognitive and academic performance, and number 2, evaluates whether a system can infiltrate 70% of the runoff we're looking at. And so for this particular portion of our project, we looked at a variety of green infrastructure, including grassy areas, gardens, bioswales, as well as dry creek bed landscaping. So for the first part of hypothesis 2, we looked at multiple studies to evaluate this relationship. And so factors considered included the physical greenness of a space, the area of green space and impervious surfaces, its proximity to the school campus, as well as students' academic performance. And so in this presentation, we're going to look at 2 of our major findings. And so number 1, with the table below and the data outlined in the red box, we find that the most significant improvement in working memory and cognitive performance came from schools having the most intense greenness and the spaces that were closest in proximity to the school. And from these charts below, we find out there's a strong positive correlation between the area of canopy cover or green spaces and the average standardized test scores. And we find a strong negative correlation between the area of impervious surfaces and average test scores. And so from these 2 slides, we see that the first part of our hypothesis 2 checks out and is proven correct. And Gonzalo will be expanding on the second part of hypothesis 2.
Yes, so for the second part of hypothesis 2, where we try to find if 70% of all runoff can be infiltrated using green infrastructure, we place grassy areas and bioswales in specific places, and then use geographical tools such as the USDA website and other government sites to determine the general makeup of the geology of the site and certain infiltration rates that have been observed in the area surrounding our school. What we then did was use the infiltration model, the Horton equation method, to actually calculate the infiltration rate after a 24-hour period to resemble sort of a saturated infiltration rate, to actually see if our system holds up to those standards. What we did also was design our improvements to be for a 24-hour, one-year storm. And using these calculations, we determined that the actual potential of potential infiltration on the site is only about 55%, which does not meet the 70% that we actually predicted. To achieve the 70%, we feel that it would be very reasonable to add more green area or just reduce the amount of impervious area on campus. The table below here shows just a difference in areas in impervious surfaces before and after green infrastructure placement. We can see here at the top row, the total, we could see 120,000 about difference between before GI and after GI for impervious surfaces, and about the same amount of increase for pervious surfaces on campus. For hypothesis 2, what we did to actually design the grassy areas and the bioswales in the gardens was actually to just place them specifically. We followed a flow pattern to be assumed of northwest to southeast to make our assumption a little easier, and just to kind of predict flow paths a little easier. We used Google Earth to actually go and check those slopes, so those slopes checked out. We did see an increase after our green infrastructure of 280% in green spaces on campus, which is great for all children, and a reduction of 30% of impervious surfaces. What we also did with the grassy areas was place them in places where no existing infrastructure was already there, such as basketball courts, tetherball courts, to have those areas still usable for the children. And here at the image to the right, we see at the bottom right, we have a proposal of the bioswale, sort of a dry creek bed landscaping, that were to use just basically some proposed gravel and sand mix and some plants to aesthetically improve the community surrounding it. Of course, California native and drought tolerant.
If our project is approved, since it is a public project, it will be funded by state and local taxes. Because of this, we prepared a general breakdown of the cost of this project. This cost estimates includes both materials and installation costs for all of the green infrastructure we plan to implement. Adding up all of our costs, it totals up to be about 2.5 million. But you may notice that our solar panels take up over half the cost. And because these panels help with energy savings, the cost will cover themselves back within 4 years per system. Although this overall cost may seem high, we believe that the benefits are definitely worth it. Not only will we be improving runoff infiltration and energy efficiency, this will also help aid the academic development of the children at Gompers. In terms of socioeconomic impacts, we believe that our green infrastructure plans will help increase property values in surrounding neighborhoods, as studies have shown that green features help improve property values. There are also many environmental impacts. By installing solar panels, we will be able to increase the energy efficiency of the school. We will also be able to increase the runoff infiltration and improve the school stormwater management using our green areas, gardens, and bioswales. Additionally, all of our green infrastructure will contribute to improving air quality. We hope you enjoyed our presentation and can now see why implementing green infrastructure is necessary for Gompers Elementary School. Thank you so much for your time.